Okay guys, in this one we're not going to talk about atomic forces so much anymore. This one is types of decay. So you notice I've left a fair bit of this here because I wanted this to stay. All of these things, all of these different types of decay are mostly based on some sort of interacting with the strong force and things being stable or not stable, and instability from this graph here. So I'm going to talk about three different regions. I'm going to talk about region A, region B and region C. Region A is where we have something that's unstable. So this, remember the white line, my curve, beautiful curve that I've coloured in like a mad person, is for things that have, it's above that stability line, so it's unstable because it's got too many neutrons. In region B, we're unstable, we're below that line, so we're unstable, we've got too many protons. As an aside, these things like to be stable because they got this beautiful proton to neutron ratio, or N to Z ratio, and when they're bigger elements, so something, say here, it wants a different N to Z ratio as opposed to something that's maybe down there. And C is just too big and fat to be stable whatsoever. Doesn't matter what we do, it's just too bloody big. And in all of those three different places, it's gonna these atoms are going to undergo a specific type of decay, and that type of decay is based on why it's unstable in the first place. So if you've got too many neutrons, you're probably going to get rid of some sort of something to do with neutrons. If you're unstable, you've got too many protons, you're probably going to want to do something to do with the protons in the nucleus, and if it's too big, you basically just want it to lose some bloody weight. Alright, so we're going to throw out some mass and hopefully that'll reduce the unstableness. So to start with, in region A, let's say we are here in region A, well and truly above that line. What we're going to have is a neutron inside the nucleus is actually going to change. Neutrons are generally, well, they're unstable by themselves anyway. So a neutron, atomic number 0 because it's got no protons at all, mass number 1 because it is, you know, a neutron, it's going to change into something. It's going to change into a proton plus something else. Alright, so what we've got to do here is conserve two things. We've got to conserve mass and we've got to conserve charge, and to an extent I'll talk about it today, but we've got to also conserve energy. Some very clever guys figured this one out. So in order to conserve mass, we need 0 plus 1 plus something is 0. So 1 take 1, I think, is 0. So what we're going to have is this new particle, beta particle, so there's alpha, beta, gamma radiation, and it's got a proton number or an atomic number of -1. So it's got a charge of -1, it's got a mass of 0. 1 equals 1 plus 0, cool. 0 equals 1 take 1, excellent. And in this case here, there was actually another particle based on energy. Mass is energy, and it is, in this case here, an antineutrino. Not a neutrino, antineutrino. In the second part, in B, we have too many protons. So inside the nucleus, the nucleon force is going to kind of shift some things around. So a proton, which is actually lighter, slightly lighter than a neutron, is actually going to change into one of those neutrons. It's actually gain mass, which is just not possible, really, but the reason it does it is because it actually draws energy out of the nucleus. Remember, I just said mass is energy, so this thing here, the antineutrino, is some mass of energy. So we can actually use some of the internal energy of this nucleus to do this one. 1 equals 0 plus 1. This one here is a beta minus particle. It's identical to an electron. This one here is a beta plus particle. It's identical to a positive electron, which is a positron. And there, and this is supposed to be a squiggly V looking thing like that, but this one here is the neutrino. Normal neutrino, weird electron. Weird neutrino, normal electron. Alright, so here we have what we're trying to do. We get something that's too high, it will lose, first of all, lose a neutron, so it'll go downwards, but it's also gaining a proton. so it's going to go across as well. So now it's heading towards that line of stability. With this one here, what it's done is gained a neutron but lost a proton. So let's say it is, I'll go blue, let's say it's this one here, too many protons. It's lost a proton and gained a neutron. So the quickest way for these things in A and B to get back to that stability line is diagonally. So it'll drop down, lose a neutron, go across, gain a proton, and vice versa. All right. For the other ones, area C, what they want to do is get rid of some mass. So I'm going to pick on uranium. Oops, 2, 3, 8. And what this thing's going to do is get rid of an alpha particle. Alpha particle identical to a helium nucleus. We write it like this: alpha, lowercase a, identical to helium nucleus. Helium nucleus has 2 protons and 2 neutrons, so 2 plus 2 is 4. So here's our particle that we're chucking out. And then it's going to change into something that makes up, remember, the mass and the charge that's disappeared from here. So 92 equals 2 plus 90. 238 equals 4 plus 234. And just so happens that number 90 is thorium. It's got a chemical symbol of that. And in this case here, we'll generally have some sort of gamma radiation emitted as well. So this one here has 0 mass, 0 charge, because it's just high energy light. Okay. So we have 3 different types of radiation that are given off because of, well, I guess there's 4 because I just said gamma as well. 3 different types of radiation given off based on this graph, and all of them will give off different types of radiation depending on where they are in this graph. Okay, they want to get back to that line of stability, and the easiest way is to lose a neutron, gain a proton, lose a proton, gain a neutron, lose some weight. All right, thanks.